Hey guys, Professor Dustin here. In this video I'm going to talk about a key example of harmonic motion, and that is a mass on a spring. So I have a mass on a spring on a frictionless surface. Unfortunately, it's very difficult to actually set this situation up, which is what I'd like to do. I'd like to show you a video of a spring and a mass actually bouncing back and forth. It's actually very difficult to construct springs which push equally hard as they pull. It's actually very difficult to do that. Even if you go on YouTube and try to look for videos, you really don't find any. So this idealized situation is actually quite hard to construct in the lab, but it's the best way of studying the system, so that's what we're going to do. So hopefully this pictorial representation is enough to get it in your head what's sort of happening. So I have a block and a spring. I put this dotted line here to mean the equilibrium position of the spring when the spring force is 0. Notice that I've put the dotted line at the equilibrium position of the spring, not of the center of mass of the block, right? Because we want to know when the spring is not stretched. So that's right here. But if this thing is bouncing back and forth like this block will have some velocity, so it's going to be heading towards that direction. As it heads that way, the spring compresses and the spring force gets bigger and bigger and bigger until it finally stops the block and starts it moving in the other direction. It passes through the equilibrium point again, and as it gets on the other side, the spring stretches and the spring force is in the negative direction, and then it starts to slow the block down and it's going to shoot it back the other way and repeat back to the beginning. So this is our harmonic process. So what I want to know is I want to know the position as a function of time of this block. So just like if I have an object which is under constant accelerated motion, the kinematic equations tell me what the position as a function of time is. I want to know what the position as a function of time is for this block. So that means I'm going to need to solve Newton's second law. So first thing I want to do is I want to get a good free body diagram. So I need to pick one of these to draw a free body diagram for and then talk about how I hope it applies to the whole thing. I'm going to pick this one to draw a free body diagram for. So here's going to be my block. I have a force due to gravity because the block has some mass, Fg. There's going to be a normal force because there's a surface keeping the block from falling down through the floor. And there's also going to be a spring force. Now the spring force right here is pulling that way, so I'm going to write F spring. I have a frictionless surface, so there's no friction here, and I think that's the end of all of my forces. So let's write Newton's second law for this guy. It should be pretty clear that in the y direction, Newton's second law isn't going to tell us anything because the block is not accelerating in the y direction, so let's just do the x direction. So in the x direction, what forces are acting? It looks like just the spring force. So that's the end of my sum of forces. Now I can write the acceleration. Mass times the acceleration. And now to rewrite this, I should really put in what the spring force is. Remember that the definition of the spring force is negative k times x minus x naught. K is the spring constant. It's given for each spring. X is the current position of the spring, how far it's stretched, and x naught is the original position of the spring, where it's not stretched. So I need to pick a coordinate system now because I have an x here. So I'm going to pick the coordinate system where x is directed positive that way, and 0 is right at the equilibrium point. So if 0 is right at the equilibrium point, I'm setting this guy to be 0. So then my spring force is just negative kx. Okay, so I'm going to put that into this equation, and I find that the equation that describes the motion of the spring is negative kx times equals ma. Okay, so this is a problem, right? We've studied systems where the acceleration was constant. There we get the kinematic equations, we can study projectile motion and other kinds of motion when the acceleration is constant. But here we have an acceleration which depends on the position. That's because the spring, the force that the spring applies to the block depends on where the block is. So this is a problem that we actually don't know how to solve. And to try to convince you that we don't know how to solve this, I'm going to rewrite the acceleration in terms of the position, right? I have a position over here. It'd be nice if I had a position over here. Maybe I could solve for x, right? Well, the acceleration is the second derivative with respect to time of the position. So I'm going to put that into the equation. Negative kx equals mass times dx squared dt squared. So now I have the definition of the acceleration as a second derivative of position. But this doesn't seem to help me very much, right? I can't really integrate this thing because I can't multiply times time and integrate over here because I don't know what to do with this x. So this is an equation. It's a special kind of equation called a differential equation. You learn about these when you take a class called Differential Equations, but that's quite a bit above where we are in this class with just calculus. So we can't solve this, but I can tell you what the answer is. And I can tell you what the answer is, and then we can check that the answer actually is that. So that's the process that we're going to go through. I'm going to tell you what x is, and then I'm going to check it for you to convince you that actually we do know the answer to this, even if we can't solve it. So we just derived the equation of motion for a mass on a spring, and we've acknowledged that we don't know how to solve this thing because we don't know how to integrate second-order differential equations. But if we knew a possibility for what x was, we could check to see if that x solved this equation. For instance, we could plug in the function here, take two derivatives, and check to see if that equals negative k times the function. But what function should we try to pick? Well, let's look at the motion of the spring to see if we can get anything about the motion that will maybe tell us what kind of equation we should put in for x. So if we just think about how the mass moves, we end up with something like this. So this is a graph of the time and the position, and the mass is oscillating between a maximum and a minimum point, passing through equilibrium, and it's very, very regular. You can think of the furthest that the mass gets away from the equilibrium, we can call that A, that's the amplitude of the motion. And of course, this motion looks very much like a function we should all be familiar with, a sine or a cosine function. Of course, it's not exactly that, right? If it was a sine or a cosine, then at 0, we would either have this point at 0, or we would have this point at 0. So this thing is apparently not exactly a sine or a cosine, but this angle right here actually tells us how far it shifted away from being actually a cosine in this case, right? Because 0 should be 1 for a cosine function. So the guess that we should use is a cosine function, and specifically, the guess I'm going to use is this. The position being a cosine omega t plus theta. So this a is the amplitude, and that theta is the phase shift. So you might not have been able to pick this out, of course, out of just using your brain, but if we look at the motion of the object, it should be pretty clear that this seems like it might be a good guess. Now the a is the amplitude, and the theta is called the phase. The t here is obviously the time, but what is this omega in here doing? Well, it turns out this omega takes a very special value. It can't be any possible value like the amplitude and the phase can be. Omega is called the angular frequency, and it's equal to the square root of k over m. It has to be exactly that value. Okay, great. So I'm claiming that this is a solution to this problem, but let's talk about what that actually means. That means that if I take this x of t, take two derivatives of it, multiply it times m, I should end up with negative k times this function again. That's what x is. So what I'm going to do is I'm going to check to make sure that that's actually true. So I'm going to evaluate each side of this equation, set them equal, and make sure that this actually solves that equation. The left-hand side is going to be pretty easy because I just need to take negative k times this. So that's just negative ka times cosine omega t plus theta. So that was pretty easy. To get this, however, I'm going to need to take some derivatives. So I'm going to start by taking one derivative of this function. First thing that's going to happen is I'm going to pass straight through the a because that's constant. Take a derivative of cosine. The derivative of cosine is negative sine. Then I have to use the chain rule to go inside of the cosine function and take the derivative of this inside part. Phase is constant with respect to time, so I just need to take d dt of omega t, so that will just give me omega. And so my final answer is negative omega a sine omega t plus theta. Okay, well, to do the right-hand side of this equation, I need two derivatives, so now I'm going to take a derivative with respect to this. The initial part's going to happen, the same thing's going to happen. Negative omega times a is a constant, that's going to pull out. The derivative of sine is now going to be cosine. And then again, when I go inside the sine function and take a derivative of this, again, I will just get an omega out of it. So my final answer is going to be negative omega squared a cosine omega t plus theta. So I'm going to go on to a new sheet, and what I'm going to do is I'm going to write down this on one side and then m times this on the other side to check to see that this is actually true. Okay, so here's that equation setting those two things equal to each other. Of course, I am sort of checking to make sure they're equal, so I'm going to put a question mark here.
So to check that they're equal, I should basically try to simplify this as much as possible. It certainly doesn't necessarily look that they're totally equal, negative Ka, negative m omega squared a. But I certainly have a cosine in both sides, so I'm going to divide both sides by cosine. And now I see that on both sides I have a negative and I have an a, so I'm going to divide by negative a. And I get the k is m omega squared. So essentially what I've just shown is that the a and the theta, they don't matter at all. They can take any value in the world because they don't affect whether this equation is true. That's a cosine omega t plus theta. This theta is buried inside this cosine. It just drops out. And also the amplitude doesn't matter to determine if this is true or not. The amplitude is also just going to drop out. But the angular frequency right here, remember I said that is not an arbitrary value. It takes a very special value, namely it's the square root of k over m. But if I put square root of k over m into that equation, I get k equals m k over m. The m's cancel, and I get k is equal to k. That shows that this equation is true. Check. I've shown that that is a solution to the equation. So although the equation of motion was too hard for us to actually figure this out from first principles, we were able to look at the graph of the motion and figure out that yes, indeed, this is a solution to that second order differential equation, and this describes the motion of a mass on a spring. So one note I want to make is that I picked cosine omega t plus theta. As you can probably imagine, that's not the only choice I could have made. There's one other function, at least one other function, that you can take two derivatives of and return back to the original function, and of course that's a sine, right? I could have started with a sine omega t plus theta, and actually the same equation would have been solved. So this is also a perfectly legitimate starting point as the equation of motion for a mass on a spring. So exactly what values this a and theta take depend on the exact process you're looking at. So in this example, in principle, to find a, we would measure the distance from the equilibrium point, and to find theta, we would measure the angular difference between 0 and where the peak was. That's a process called setting initial conditions, which we'll get to when we start looking at actual examples of these. For the moment, we just want to think about the equation of motion being a cosine omega t plus theta or a sine omega t plus theta. So before finishing up, I want to talk about the fact that this motion is repeating itself, and therefore we can say that this motion has a certain period associated with it, the period over which it takes one cycle to happen. That's essentially the time difference between two subsequent peaks. And if I label that as T1 and T2, I can call the period the time difference between T1 and T2. Well, I can relate this back to the other physical quantities of my system because I have a cosine function here, right? So between T1 and T2, what happens inside this cosine function? Well, the phase inside the cosine function has to increase by 2 pi, right? It has to increase by 360 degrees because we know that the cosine function is periodic with a period of 2 pi. So whatever the phase of the cosine function is at this t2, it's just omega t2 plus phi. It has to be 2 pi bigger than the phase of the cosine function at t1. So I'm not really saying that I know very much about what omega and theta is, but I am saying that I know that the phase must increase between t1 and t2 by a factor of 2 pi. Well, look at this equation, right? I can actually subtract theta from both sides, and then I can actually collect the t1 and t2 terms together so that I get something that looks like the period. So I can do that by subtracting omega t1 to the other side. I get this, and now I'm going to pull out an omega. There's my period right there, t2 minus t1. And I find that I get omega times the period is 2 pi. Well, I know what omega is right here, so let's bring that to the other side and rewrite it in terms of square root of k over m. And I find that the period of the motion is 2 pi times the square root of the mass of the block divided by the spring constant. So using just the knowledge of m and k, I can figure out what the period of the motion is without having to go through all of this stuff. So because I know generally the harmonic motion equation, I can figure out what the period is immediately. Okay, that's it. So this has been an introduction to a mass on the spring. We've figured out what the equation of motion is up here. We figured out that the angular speed is this, the period is this. And we talked about finding A and theta is a matter of knowing what the motion is and measuring the distance and the phase shift, and that's called setting initial conditions. Okay, guys, thank you for listening, and I will see you next time.